The following is an example of exponential decay that involves the concept of half-life. A radioactive material decays according to the exponential function m equals a multiplied by e to the power of kt. If the initial mass is 500 grams and the mass after 10 months is 400 grams, find A, the half-life of this material, and B, the rate of decay at the half-life. So for part A, we know the initial mass is 500 grams. That comes from the question. So therefore, A equals 500. So that's fairly easy to solve. So that's the coefficient of the exponential function there. Now we also know that the mass, m, is 400 grams when t equals 10. So at the 10-month mark, the mass of this material is 400 grams. So substituting m equals 400 and t equals 10 into the exponential function and solving for k. If we divide both sides by 500, we have 4 over 5 equals e to the power of 10k. Taking the natural log of both sides, so that's log to the base e, we have ln 4 over 5 is equal to 10k. Making k the subject of the formula, so dividing both sides by 10, we have k equals 1 over 10, or you can say ln 4 over 5 all over 10, but I just expressed it in this form. And I'm going to leave k in exact form, not going to round it. If the question asks for rounding, then just round it according to whatever number of decimal places or significant figures the question asks for. But I'm leaving it in exact form in this case. Now the half-life is the amount of time it takes for half the mass to decay. So if we're starting off with 500 grams, we're interested in how long it's going to take for this 500 grams to become 250 grams. So substituting 250 for m, obviously A is 500, so that's our initial, the initial mass of the material. 250 equals 500 times e to the power of kt. We have the value for k already, so I need to keep this handy, so I'll be using this value shortly. And we need to solve for t this time. So dividing both sides by 500, we have half equals e to the power of kt. Taking the natural log of both sides, so we have ln of half is equal to kt. And dividing both sides by k, we have t equals ln half divided by k. And evaluating this, we get t equals 31.0628372 months. So I didn't round that one. So it's around the 31-month mark that half of the material will decay. Now, if we wait another 31 months, or roughly 31 months, this 250 grams will become 125 grams. So it keeps halving every, or roughly 31 months. The mass halves each time. So that's the concept of half-life. Now, for part B, the rate of decay at the half-life. So dm dt is equal to kp. And we know that P is equal to 250. So at the half-life, the mass of the material is 250. So we can substitute this value directly into this differential equation. So P is equal to 250. K is this value here, which we've evaluated earlier. And just evaluating Kp, so dm dt is equal to 1 on 10 multiplied by ln 4 over 5 multiplied by 250. And we get negative 5.58 grams per month. So that's the instantaneous rate of change, correct to 3 significant figures.